Okay, let's start. Thank you very much for being here. Let's remove. So, this week we have Paula Izquierdo, who will be visitor. That's going to be at least till December. She will be an on-off visitor, but you can find her in the office next to the Students Plus, some postdocs office. And actually, she's from nearby. Where's the village where your family is from?
Yeah, my family is from Teruel, but I was born in Valencia, and right now I am in University of Warwick, near Coventry. But yeah, my mother's village is near.
So she did the PhD at the AEC with Pablo Rodriguez Gil, and the co-supervisor was Boris Gensike, where she is now in Warwick doing the postdoc, remote postdoc. And today she's going to talk us about white dwarf traces of evolved planetary systems. So,
yeah,
all yours.
So, hello everyone. Today we are going to learn what we can obtain from white dwarfs in order to learn about evolved planetary systems.
Working? Yes, no? Yes.
Okay, so we are going to start giving a brief introduction about the great potential of white dwarfs and their general properties. Then I will give a brief note onto the odds of planetary survival from the main sequence towards the cooling track of white dwarfs. Then I will talk about the main mechanisms for pollution delivery and also about the signposts that these evolved planetary systems leave in white dwarfs. Then we will move to what can we learn from these systems and how to do that with methodology to employ. And finally, we will end by getting to know what we have learned from these systems and what to expect from the future. Okay.
Maybe we have to change the batteries.
So even though we know more than 5,700 exoplanets, and the studies claim that between 30 to 70% of stars may host a planet, we still know little about these exoplanets. This is partially due because we are limited by the methodology that we employ. In particular, the main methods that we use to unveil population of exoplanets are transits or radial velocity, which are biased towards closing big planets. This is what we can see in the sample of confirmed exoplanets with estimated mass and orbital separation that we have in this plot. And also, what we know about the inner constituents of those exoplanets is also little, because right now we are guessing what's inside from the mean density of these exoplanets. We get to know the mass and the radius, and from models of planetary formation, we derive a mean density. But how can white dwarfs help to unveil this information that we are losing? From the theory of stellar evolution, we know that all the stars that have initial main sequence masses below 8 to 10 solar masses will eventually become white dwarfs. And from an inspection of the sample of host stars, when I mean host stars is the stars that are hosting exoplanets right now, we can see how almost every single of these stars are going to evolve into white dwarfs. So a priori, it seems a good idea to go to white dwarfs to study the exoplanets that we might be losing. In fact, 95% of stars in our galaxy are to evolve into white dwarfs. But what are these objects? White dwarfs are Earth-sized stars, but with mean masses of 0.6 solar masses. This great or big mass containing such a small space causes high surface gravity that in turn translate into metals. From now on, metals are everything that is heavier than helium, to sink out of the photosphere of the white dwarf in timescales that are much smaller than their cooling edges. These high surface gravities and this rapid sinking of the metals translate in typical pristine photospheres of white dwarfs. In particular, the blue spectrum that we can see here is the most typical spectrum of a white dwarf, those that are dominated by Balmer lines. These are called DAs. Then we have the second most populated group, which are the DBs, dominated by helium-1 transitions. And finally, we have other flavors of white dwarfs, but the third most populated are the DCs, which are featureless. This is the theory, pristine photosphere, but what was the surprise when we started to find loads of pollution in loads of white dwarfs? In particular, here in the top panel, we have the spectrum of the first discovered metal-polluted white dwarf. This is called the Bamanen 2 star, and in particular, the first evidence of an exoplanet has been revisited and it is now attributed to this metal-polluted white dwarf. We will see how this metal-polluted can be linked with exoplanets in a few slides. This first observational evidence has been revisited in part due to this photographic plate taken in 1917, where we can already see the H and K lines. There's loads of pollution. In particular, the statistical studies are saying that between 25 to 50% of white dwarfs should display metals. Now, I will tell you how these metals get into the white dwarf, and now we move to the odds of planetary survival from the main sequence towards the red and asymptotic giant branches, the main mechanisms for pollution delivery, and the signposts of evolved planetary systems. The planetary survival is a competition between the tidal forces, which try to pull the planets in, and the mass loss that the star experiences when it leaves the main sequence toward the red and asymptotic giant branches, which causes an orbital expansion. In short, and because there have been several studies about distinct planetary architectures and for different stars with different masses, but for one solar masses, we know that terrestrial planets beyond 2 astronomical units, gas planets farther away than 3 astronomical units, and asteroids farther away than 2.5 astronomical units should persist through the evolution from the main sequence towards the cooling track of the white dwarf, and hence arrive to the white dwarf phase. Sadly, this planetary survival comes at an expense of a reduction of the orbital stability because of all the evolution that the planetary system has experienced during this evolution. And this reduction of the orbital stability, what causes in the main cases is for the big perturbers, so the bigger bodies, to perturb the smaller bodies of the survival planetary system and to make them pass nearby the Roche radius of the white dwarf, where they will be shredded by tidal forces and eventually accreted onto the surface of the white dwarf. This is the main mechanism for pollution in white dwarfs. This is gravitational scattering from perturbers from one lunar mass, but there are other mechanisms, as can be the increasing luminosity that white dwarfs experience at the beginning of the cooling track, that can cause some spherical bodies to rotate up to the breaking point, and then they will be shredded and be dragged towards the photosphere of the white dwarf by means of any radiative drag process. Once these a small body has passed really nearby to the Roche radius of the star and has been spread, we have planetary debris. Okay, so sorry, here we have a schematic of the debris accretion onto white dwarfs. So we have the planetary debris that gets circularized into an accretion disk, and eventually it is accreted onto the surface of the white dwarf. As soon as it is accreted, the metals start to sink out of the photosphere with particular velocities depending on each element. Depending on when and how we observe these white dwarfs, we may find one of the different signposts. The first one, we have already talked about it, is the metal pollution seen in several white dwarfs. To do that, we have to obtain a spectrum of the source, and here we have an optical spectrum of GD44, a highly metal-polluted white dwarf that we identified several years ago. And even though we just have the bluest optical spectrum here, we were able to identify 11 metals here and derive the chemical composition of the exoplanet accreted. On the other hand, if we go to archival photometry and we can construct the spectral energy distribution of the source, in some really lucky scenarios, we may find that there is an infrared excess, and if we discard other possibilities, we may link it to the presence of a dust disk. In particular, we are employing this technique in order to look for possible candidates of metal pollution, because if there is a dust disk, it most probably presents a metal pollution. Here in this plot, we have GD16 and a metal-polluted white dwarf that presents a dust disk. The third signpost is if we are super lucky, because these are really rare systems, and is the presence of double peak emission lines that are originated in a rotating Keplerian disk. In particular, these double peak emission lines, the blue shifted peak comes from the gas that is moving towards us, and the red peak is the gas that is moving away from us. And this tells us that there is a gas disk apart from the debris disk. And finally, maybe the most striking signpost for the people working in my field, because it's supposed the final milestone for all the theoretical background about planetary systems, about white dwarfs, was the discovery of transiting material passing in the line of sight of some white dwarfs. In particular, this light curve belongs to the first transiting white dwarf 1145 plus 017. And in this light curve, we can see two main transits, transit A and transit B, with a complex substructure that we later were able to model. So these are the four signposts. And now we move to what can we learn from these systems and how to do that. I'm going to start with how to get the chemical composition of the exoplanets. Okay, the first thing in order to obtain the parent body compositions is to characterize the white dwarf. So the first thing that we have to do is obtain the effective temperature, surface gravity, and overall chemical composition. There are several techniques, but the main two ones are, well, I'm going to start with the photometric method, which is retrieve archival photometry, construct the spectral energy distribution, and model that spectral energy distribution with a white dwarf model. From them, we can obtain the effective temperature and surface gravity. This type of modeling is not really sensitive to the changes in the chemical composition. And at the end of the day, you will have to go to spectra because you want to get the chemical composition of the exoplanet, so you will have to go to the spectroscopic method too. How to go to the spectroscopic method? The helium and hydrogen lines are sensitive to the changes or to the conditions of the photosphere, and hence we can model those lines in order to get these parameters. Once we have obtained these three parameters, we fix them in order to compute models now with the metals that we have been able to pinpoint in our spectrum. Once we have done that, we will have obtained the photospheric metal abundances in the white dwarf. How to translate them to the parent body composition, so to the composition of the accrete body? Okay, to do that, we have first to compute the diffusion timescales. As I have said before, metals sink out with particular velocities. These diffusion timescales are dependent on the mass of the convection zone, the depth, the chemical composition, the characteristics of the white dwarf, and also the particular velocities of each element, which depend, for example, on the atomic mass. So once we have computed this, if we go to this formula, this is what we measure from the white dwarf. So this is the photospheric metal abundances, and this is what we want, the metal accretion rates, because they are mirrored in the parent body compositions. So in order to go from here to here, we need the diffusion timescales, which I have already explained, how to obtain the mass of the convection zone. At this step, we already know it. And we are left with the most tricky part, which is assume at which time started or stopped the accretion. This is the most horrendous case. And in a simplistic scenario, we assume that accretion started some time ago. It has had a uniform rate of accretion, and it stops at some time. Like we don't have like on and off. Okay, in this simplistic scenario, we have three accretion states. In the first one, which is called the increasing state, before accretion starts, we have a pristine photosphere, so helium or hydrogen or a mix of them. And accretion starts and metals start to build up in the photosphere of the white dwarf. In this state, we can, like the parent body compositions are more or less those as we see in the photospheric metal abundances. Then at some point, when accretion has been going for some years, we would say, an accretion diffusion equilibrium is reached in which the metals are being accreted onto the white dwarf at the same rate as they sink out. And in this state, which is called the steady state, is the only one where we can reliably derive the parent body compositions. And finally, the decreasing state, which is the most tedious, accretion stopped some time ago. We don't know when. We have to assume a lot of things because, for example, let's say that we look at a white dwarf and we see that there is magnesium and calcium, but at the beginning of the times, iron was also accreted, but it has a really fast sinking time, so we have lost that information. How to know in which accretion state we are? Well, good luck. If you find a debris disk, we can say we are most likely in the steady or increasing state because we still have the source of pollutants, and we can say, okay, it must be ongoing accretion because we are able to see the metal pollutants and we have the source of them. But if we do not detect that disk, things start to get more tricky. This analysis was firstly performed by Zuckerman et al. Back in 2007, where he studied a highly metal-polluted GB361 and derived a chemical composition for the accrete exoplanet of a composition resembling an Earth-Moon system. Here we have the elemental abundances by number relative to silicon. Okay, we are in the position now to also look for water-rich accretions. In order to do that, we have, what we do is compute the budget for metal oxides. Here it happens the same as in exoplanetary science. We cannot look for life if we don't know how that life looks like, so we look for the same biomarkers that we expect from the Earth. Here we do the same. We know the minerals that are forming the solar system, so what we do are maths of if we find so many magnesium atoms, we say they should pair with so many oxygen atoms. We do that for all the minerals that we know. We do those maths. We get a conservative approach because, for example, in the case of iron, we know that in the solar system, it presents in the mineral form, but also in its elemental form. So after the conservative approach and doing that maths, that computing that budget, if there is any oxygen excess, well, sorry, because I forgot to say this, for that we have to be able to detect oxygen in our spectra. In most of the cases, we don't detect oxygen, but if we detect oxygen and we have done these first two steps, if there is any oxygen excess, we might start thinking about a possible water-rich accretion. This claim gets stronger if we can locate or detect trace hydrogen. If we have a hydrogen-dominated photosphere, this is impossible because everything is hydrogen, but in some cases we are dealing with a helium-dominated photosphere. In that case, since hydrogen is lighter than helium, it never sinks out. And if we can discard what or which part of that hydrogen is primordial, some of it can be accreted into a water-rich accretion or water-rich from a water-rich planetesimal. What can we learn about the architectures of this? As we have seen, there are some rare systems that show the presence of double peak emission lines. And the main application that we have found for them is to reproduce or to reconstruct the space distribution of the gas disk. Someone can.
Yeah. Everything is under control.
Okay. How can we do that? We can do that with a technique called Doppler tomography. This technique uses the one-dimensional velocity information encapsulated in the double peak emission lines to produce a two-dimensional image of the disk in velocity space. The formation of these line profiles in a particular phase can be thought of as a projection or a collapse of the image of the disk along the direction defined by this orbital phase. This is what we can see in this plot. In order to do Doppler tomography and to be able to construct or reconstruct the space distribution of the gas disk, what we need to do is observe this type of systems in several epochs, so we are able to track the evolution of the double peak emission lines. This is what they did in this study, and in the left plot we have some of the continuum normalized spectra of the calcium triplets. Sorry, I forgot to say that these are the most common double peak emitters in white dwarfs, the calcium triplet. And with that, they were able to reconstruct the gas distribution. What can we learn if we study the live body disruption that I showed you in one of the light curves before? Well, the first thing that comes to our mind is that we can track the debris fragments in order to learn the periodicities of these debris. In this plot, we have the sum of the optical light curves of white dwarf 1145 plus O17 folded on its fine period. This is by far the most studied white dwarf because it was really bright. It was visible from ground telescopes, like amateur astronomers were also looking at them and providing lots of light curves. And what can catch your eye, is that the transits are rapidly evolving. This is there's 1 night separation, and when you try to track them, it's quite difficult because they are rapidly evolving and they are not symmetric. So we had to come up with a technique to model these asymmetric transits. We didn't do that. It was Rappaport who was trying to model cometary tails, so we took his insights and knowledge about this, and we started using asymmetric hyperbolic seconds to model this type of transits seen in white dwarfs. This is not for white dwarf 1145, but for the third transit in white dwarf found it. Why using this technique? Because it allows us for a lot of freedom. It comes with 6 free parameters, in this case the out of transit flux, the number of asymmetric hyperbolic seconds, and a scaling factor, and the 3 times the time of minimum flux, which is what we need in order to look for a periodicity, and the ingress and egress times. Usually what we do is in the first transit that we see for the first night, because we see several transits from several fragments, we let all the parameters free, and for the subsequent orbits, we keep the out of transit flux and the number of asymmetric hyperbolic seconds fixed. So we preserve the form or the shape of the transit, but we allow for a bit of freedom. Okay, until here it has been the theoretical background and the methodology employed, but we move to what have we learned so far. About the chemical composition of exoplanets, we have learned that there is lots of pollution. So far, we have identified more than 1,500 metal-polluted white dwarfs, but sadly, most of them, as you can see in this histogram versus the number of metals detected, most of them just display the presence of one metal. In particular, what we need are the more metals, the merrier, because if we want to proceed with this study of the chemical composition of exoplanets, if you just have one element, there's no much that you can say. And as you can see, there is little objects with enough elements to do great science, let's say. If we talk about the frequency of metal detections, I don't know if I have already said it, but the most detected metal by far is calcium. As you can see, we have more than 1,400 detections. This is due to the H and K resonance lines of calcium, which are quite wide, deep, and hence, and also they are in a wavelength range that is covered by several spectrographs that map the sky. So it's really easy to detect them. We can use all of these detections in order to target this metal-polluted white dwarf that we are just seeing one metal in order to look for others if we go for higher spectral resolutions and a higher signal noise. In particular, I think you can, Carlos, with J plus and J bands, you can find the H and K lines. You are sensitive to that. Calcium is followed by magnesium, iron, silicon, and sodium, I would say. And then we have chromium also, and then we have more exotic elements. Maybe you are wondering why we have hydrogen detections. This is in all the cases that we have a helium-dominated photosphere and we are able to detect the trace hydrogen. In terms of what have we learned of the parent bodies that have been accreted onto the white dwarfs, is that most of them are rocky and dry, and they resemble the objects that we have in the inner solar system. In particular, in this plot, we have the study that we performed to GD424, the metal abundances relative to silicon for the parent body that this white dwarf accreted, compared to the metal abundances relative to silicon in the bulk Earth. In this case, and in most of the cases where we have performed this in-depth analysis of the chemical composition, we cannot differentiate between a bulk Earth composition or CA chondrites, which are these short dash line, because we don't have sodium detections, neither carbon, which would be the difference between them. What we have learned is that even though they are solar-like, we have found lots of diversity. As I have mentioned, we performed the study of GD44, and here you have the, well, in bars and in colors, the composition compared to the bull curve. In this case, here we have the bar for chondrites, no CA chondrites, which they are really resembling to, but we have found some more exotic accreted bodies. In this case, for this white dwarf, they found that it resembles, that it has accreted a body such as what we expect for the core air. I haven't used this. Okay, yeah, I can use it. And in the case of this white dwarf, they concluded that it has accreted something resembling what we expect for the mantle Earth. And finally, and we will see this a little later in the slides, but in particular, this white dwarf shown a really special composition, and they concluded that it has accreted a planetary body resembling the chemical composition seen in the comet Halley. In this plot, we have two of the most extreme spectra that you can find in metal-polluted white dwarfs. In particular, in the top panel, we have a white dwarf that should have accreted a crash-rich object in order to show all of these metallic transitions, where they are dominated by calcium. Some really, this will translate into really small metal abundances of iron. We have some titanium and a lot of sodium, yeah. And then on the other hand, on the other extreme, we have how a white dwarf would look like if it accretes a core-rich planetary body with loads of iron transitions, some nickel, magnesium, and smaller transitions of absorption lines of calcium. What have we learned so far about the accretion of water-rich planetesimals? Even though we have found more than 40 white dwarfs with oxygen pollution, so we are able to see oxygen absorption lines, we cannot claim an unambiguous detection of a water-rich planetesimal. Why? Because we have to check a lot of checkpoints. In order to claim for an unambiguous detection of a water-rich planetesimal, we need an oxygen excess, we need to identify a debris disk, so we can say we are in the steady state where we can say for real this is the parent body composition. And if we are really lucky, we can look also for trace hydrogen. So we have to be with helium-dominated white dwarfs, oxygen excess, dusty debris disk, and loads of trace hydrogen. This has led to just 4 unambiguous detections. In the first case, the most recent one was the claiming for an accretion of a giant icy planet made by my boss in 2019. I will talk about it a bit more later. Then CE claimed the accretion of a Kuiper bell-like body. This is the bar that we've seen before with the comet Halley comparison. And finally, the most old ones, so the first discoveries of a water-rich accretion were made by Roberto Raggi and Jay Farihi, where they were dealing with a helium-dominated white dwarf with oxygen excess, dusty debris disk, and some trace hydrogen. What have we learned about the architectures of this? The first thing that we have learned is that the disks are quite rare. In particular, just 1 to 3% of all the white dwarfs that we have studied display infrared excess that we can link to a dusty disk. Why? Because we have to discard other possibilities such as brown dwarfs or other type of companions. And even rarer are the white dwarfs that display emission features. In particular, this is 0.07% but the person who got this statistic is a collaborator, and we were revisiting this because we are working together in a collaboration, and we know that this number is even smaller because we were biased with the sample that we used there. So they are even greater. This makes a total number of published emission line systems of 21. But just 2 of them have had an extensive study which allowed to reconstruct the space distribution of the gas disk. In particular, we are looking for promising candidates such as the one that we have in the. I have a problem with left and right, so here, okay. This is one of the most promising candidates because it shows double peak emission lines from a lot of metals, in particular from iron, magnesium, oxygen, calcium, and also from hydrogen. And why this is important? Because if we are able to obtain the metal abundances from the gas disk, we will be able to compare those with the photospheric metal abundances that we get from the white dwarf spectra, and then we can compare how good we are doing in terms of deriving the composition of the parent body. So like a double check. That's why I was asking before about Claudio. Employing these double peak emission lines, we have been able to unveil the presence of a rigid body embedded within the debris and gas disk of one of these rare systems. This was a study presented by Chris Nancer, a collaborator, in 2019, and this was possible because we produced a tree-less spectrogram, so we were tracking the evolution of these double peak emission lines, and we subtracted from the full of them the mean spectrum of these lines and got a residual signal of a sinusoidal, which can be linked to a point source in a rotating disk. We have talked about the accretion of this giant icy planet. In particular, what they did was employing or using the double peak emission lines of sulfur, oxygen, and calcium in order to derive the chemical composition. And they concluded that this system have accreted material that resembles the deeper atmospheric layers of icy giant planets with water and hydrogen sulfide, I think it's red like that, being the major constituents. What have we learned about the light body disruptions that we have been studying? We have learned that transiting white dwarfs are quite rare. So far, we just have 8 published systems, but just 5 of them we have been able to measure the orbital periods, because in some of them we have just been able to locate one transit, and we are waiting. We are doing photometric follow-up and also spectroscopic follow-up in order to see if they are metal-polluted. As I mentioned, white dwarf 1145 plus 017 has been the most studied white dwarf, and from it we have learned, because right now a second white dwarf is displaying the same behavior, is that transits tend to dim and disappear after a few years of collision. So what we see in this planetary debris disk is that the big fragments are in ongoing collisions, and they produce loads of small pebbles and dust, and this obscures the surface of the white dwarf. And right now, if we observe white dwarf 1145 and other transiting white dwarf, what we see is a flat light curve. We cannot know if our assumption is the good one because we don't have information about the source before it started transiting. What we can also do is model complex superstructures. In this case, this belongs to the light curve that I show you as a foreign signpost. This is the transit B, the deepest transit detected for a transiting white dwarf, where we were able to see a complex superstructure, and we modeled it with these asymmetric hyperbolic seconds that I told you before, and concluded that it was consistent with 6 equally spaced fragments or a really unlikely inhomogeneous cloud. And another approach that we can do with these transiting white dwarfs is derive the size of the constituent that cause these transits. For this, they use the Armstrong exponent technique. And what you do is looking for the depth or for a change in the depth of the transits in different wavelength ranges. If you don't find anything, as we did with this study, you confirm the great transits, and in this case, it translated into lower limits for the particle causing these transits of 0.5 to 1 micrometers. What can we expect from the future? What we want from the future are more objects, because as we have seen, we have loads of metal-polluted white dwarfs, but some of them just display the presence of one metal, either because we haven't looked at them with the proper instrument, so higher spectral resolution and higher signal to noise, but some of them just have calcium. So what we want is the bigger samples, the more exoplanets. So far we have from Nicola, who used the Gaia information, he derived a catalog for white dwarfs with 360,000 candidate white dwarfs, but less than 10% of them have a spectra. So less than 10%, we know that they are for sure white dwarfs. What we want to do is target those candidates in order to retrieve their spectra and see how many of them are metal polluted or have transits or have gas disks. I am involved in the DESI collaboration. Even DESI has nothing to do with white dwarfs. We are targeting them when we are in bright time and they cannot look at their galaxies. And so far, in the next data release, which is going to be the first one, we have observed 50,000 white dwarfs, and we have new 800 metal polluted systems, which is super interesting. In the plot, we have the Hertzsprung-Russell diagram showing the white dwarf sequence obtained by DESI with all the metal polluted systems overplot. I am not part of WIP, but I think Carlos is part of WIP. And it is expected to observe 60,000 white dwarfs. I don't know how many of them will be new identifications and how many of them were of this part of 8.5% that already have a spectrum, but we expect some new systems if we are to derive the same numbers as from DESI, which 80% are new identifications. Sorry, I forgot to say that. And finally, we have also SDSS, which in the data release 19 observed 15,000 white dwarfs, and among them we found 100 metallic systems. This is the most promising metal-polluted one of the most promising metal-polluted white dwarfs that we have found in the CDR1. Why is it so promising? Because we have a helium-dominated atmosphere, we can see hydrogen lines, we have loads of metals, and we have to take into account that this is DESI. It doesn't have the greatest of spectral resolution, so if we point to this source with another instrument with better capabilities, we are with great odds to find the presence of more metals, and we already can see an oxygen absorption line, so fingers crossed for an oxygen excess and maybe another water-rich planetesimal. Among DESI, we have also been able to identify 6 new emission line disks. So this increases the sample by 20% of the already known them. I personally do not do a lot of science with emission line disks, but the person who was like the pope of emission line systems has left academia and has given us the task to do them. So stay tuned because maybe this is my next work. And in terms of the transiting white dwarfs, we have little systems, and what we are realizing is that there is variability in 3.4 micrometers. So we are using from ZTF and Gaia the anomalous excess scatter in order to identify new candidates. So far, we have new 84 high confidence near infrared variable white dwarfs, and we are photometrically and spectroscopically following up these systems. And from the top 7, one displays, apart from transits, a metal-polluted spectrum, so one new remnant planetary system. This is the end of my talk. So what we have seen is that white dwarfs provide the unique opportunity to unveil the chemical composition of exoplanets, because from exoplanetary science we just know mean densities. What we have learned so far from this chemical composition analysis is that most foreign bodies resemble what we have in our inner solar system, so bodies that are rocky and dry. We have been able to find some exotic systems that display clues for an accretion of water-rich planetesimals. We have also seen how the emission line systems can be used to track or to discover new exoplanets, and how we can do great science with the studying the life tidally disrupted bodies that we see in some transiting white dwarfs. And what I want you to take home is that we need more data, as every good scientist would say, because we want more objects to do proper statistics and to compare with all the knowledge that we have about the formation of planetary bodies. And that's it. Thank you.
Thank you very much, Paula. Very nice talk. Question? Elena?
Thank you, Paula. Very interesting. It's a field completely new to me. So I was wondering the conclusion that most of the observations come of the pollution comes from rocky planets. Could that be biased because maybe the gas planets live for a shorter time? The accretion of those planets, I mean.
You mean that they do not get to the face of the white, or to the white dwarf face, or that
the time scale for being
the diffusion
observed,
time scales of the elements are smaller?
Yeah, that's what I was wondering.
It might be the problem. Well, we are really biased. For example, right now, if we are really lucky, I mean, we have a great number of metal-polluted white dwarfs, but it's a small number compared to all the white dwarfs that we know. And the first thing is that the most typical white dwarfs are hydrogen dominated, and the diffusion timescales in hydrogen dominated white dwarfs are from 1 to 2 years. So it's a really small time to see that pollution, even though we know that the lifetimes of the disk are from 10 to the 4 to 10 to the 6 years. So we have a small window to see this metal pollution if we are dealing with hydrogen dominated white dwarfs. This is one thing. The second thing is that we are able to see more metals because the opacity of helium is smaller than that of hydrogen in helium-dominated white dwarfs. And in helium-dominated white dwarfs, we have this problem that I mentioned about the decreasing phase, which is the most hideous because we have to assume a lot of things. So I know we are super biased, and it might be that we are biased towards that, but I don't know a lot about giant planets, but what are the main constituents? Apart from the giant icy planet, I don't know more. What are the main constituents? You know? Already?
For Saturn and Jupiter is hydrogen and helium.
Well, in that case, we cannot say anything for hydrogen and helium because we are dealing with hydrogen or helium white dwarfs, so it's little what we can say. Yeah, we could be really biased towards rocky planets. That's true.
So I was gonna say that when the star went into the giant phase, it might have evaporated the icy moons or icy objects. So maybe that we get left with the rocky remains.
Yeah, well, it depends on the position of those gas giants and also in the position of those rocky planets, because in the red and asymptotic giant branches, all of the ones that are really nearby to the star are going to be left. So that's another thing why we don't get as many pollution as the statistical studies claim.
Because it's easier to actually perturb a small rocky planet, right?
Hmm.
If Jupiter survives, you can hardly imagine something in our solar system that can perturb Jupiter and send him inwards. Whereas you can easily imagine Jupiter sending Mars inwards.
Very nice talk, Paula. How do you know that all the metals that traces that we find, they are coming from exoplanets? There is another hypothesis, like white dwarf non-sequencing stars, for example.
You mean like a companion of a main sequence star? Yeah, it can be, but in that you are talking about white binaries?
No, the compact binaries. I mean, I just like asking.
Yeah, but in that case, we will see other.
Yeah, that's because I had the feeling that since the beginning we have assumed that all the metal traces you find are coming from exoplanets.
No. In fact, the first clue, well, this has been an ongoing discussion. In the beginning, they were finding metal pollution and they were thinking it was a core drag, so it was coming from the core, but we don't have enough convection at those stages in the white dwarf to explain that dragging from the core for the metals to be there. Then they were thinking about interstellar medium to be the source pollutant, but some studies have been performed in that field, and we haven't been able to locate like metallic, like really rich ISM clouds that can explain the metal pollutants that we see. And in the case of other companions, I assume we will see other signposts of the companion, not just the metal pollution. But it has been an ongoing process. Like it was just in 2007 where the first study came, and he was the first one to say, "Hey, what if this is coming from a shredded planetesimal?" And then all this started to develop. But we were thinking about a brown companion, a brown dwarf, and some interstellar medium and other possibilities.
Okay, Alejandro, you can unmute yourself.
Hello?
Oh, no? Can you hear me? Not?
Yes.
This is Lumbrera.
Okay.
Yes.
This is Lumbreras, yes. I'm sorry not to be there, Paula, the day that you come. I hope I can catch you at some other time.
Yeah, see each
very,
other.
Yeah. Very nice talk. Very interesting topic, very crazy. The first time I heard about it, I think it was through you, and it was very surprising. But I wanted to ask, well, the first thing that I have to ask is emission lines. How strong are the emission lines? But I think you showed a plot in the very end, and it looked like they were way way softer than the absorption noticeable. So if this is the typical of the emission lines, and I can forget about the lines.
We can forget about it.
Can you repeat, Alejandro, because your connection is not
Probably his
stable?
technique in picking up emission line objects.
Yeah.
Well, I assume
Yeah,
Sorry?
I was asking about the emission lines. If all of them are so soft, so not so noticeable as the absorption line.
Yeah, we just have 21 published systems with emission lines, and 2 of them have really strong emission lines, but the remaining are as soft as these ones. Right now, what we are doing in order to try to track not to track them, but to pinpoint more possible emission line emitters or systems is to compute the equivalent width in that region and to look for an anomaly there. So using that technique, we have been able to identify 6 new emission line risks in DESI, but yeah, they are super soft, and there's little that we can do with them. Like, well, for sure with DESI, like we don't have neither the signal to noise nor the spectral resolution to do anything, but we should go to other instruments to get a better spectrum and also to track them to see if we can, for example, reproduce the distribution of the gas disk or other science.
Okay. Thank you.
Thanks, Lee.
Thank you very much. It was a very interesting talk. So my background is galaxies, not white dwarfs. So sorry if or exoplanets. So I'm curious. At the start, you mentioned that most exoplanets are present around white dwarfs, right? So most of the observed exoplanets were around white dwarfs. You mentioned. What did I?
No.
Okay,
What I meant is that all the main sequence stars that right now have been found to have exoplanets at some point are going to evolve into white dwarfs. So that's why that's one of the potentials of white dwarfs. That if we are not getting this information from main sequence stars, maybe we can move to white dwarfs to see if we can retrieve this information lost. But no, right now there is one candidate, white dwarf, with a planet, and it is really dubious. And if you count as a planet the science that I presented later with this this rigid body embedded in the debris and gas disk, it can count, but I wouldn't say anything. That's it. That's a dead planet. I think I always say I studied dead planets.
Thank you.
Yeah, around dying stars also. Everything is dying.
More questions?
Well, his question made me wonder, like, have these kind of studies been done in binary systems where maybe the solar wind or something from the companion star is accreted to the white dwarf to see if we could detect the hydrogen and helium?
Yeah, right now there is a pioneer study which is using white binaries. Well, it is related to what you are saying because I don't know about white binaries, but what I remember from that study is that in binaries they tend to be born with the same chemical composition. So they wanted to check how. I remember now. So stars in a binary system are born with the same kind of chemical composition, and the formation of the planetary system is from the same cloud. So they are assuming the planetary system has the chemical composition of the born star. So they were trying. There's just one system. They have just been able to locate one white binary with a metal-polluted white dwarf and a main sequence star. So they are using this as a pioneer study in order to look for more systems to check this theoretical background. If the parent body, the chemical composition of the parent body that we derive can match the composition in the main sequence star that is the companion. That's what you were saying?
Yeah, exactly.
Yeah.
I have one question.
Go for
Correct me if I'm wrong, but
If I can.
this pollution phase should be present in every star like the sun with planets around when it becomes white dwarf, no? So
No. I mean, it depends. That a star right now in the main sequence has an exoplanet doesn't mean that it's going to be a metal-polluted white dwarf, because maybe the exoplanet that it has is beyond the limits of the existence of exoplanets.
Yeah, if they are within the limits to be accredited, then they will show this pollution.
This pollution doesn't come from the red and asymptotic giant branches accretions. This pollution comes from the accretion that they suffer during the white dwarf phase. So if they have survived this,
Okay.
we can, if they have survived this and they are perturbed and they go within the Roche radius or they are these other mechanisms that I taught, we can see metal pollution.
So the question is, will the sun show pollution when it becomes a white dwarf, or we don't know?
Hopefully, likely, I don't know. Likely. The sun is
According
going
to the slide, we're not gonna be there, right? So Earth doesn't survive.
Will we be able to detect water in the polluted materials of the sun?
I would say if
Or
there
not.
are surviving meteorites, asteroids, yes, but not from the rocky planet that we are living right now, because those are going, well, in most dynamical studies, they are going to be eaten in the red and asymptotic giant phases. So
So
not from them.
that means
Maybe
that
a giant icy planet accretion, no?
so that means that if you detect one system, that means that there are many systems that have water
Yeah.
for one to be to meet these conditions, no?
I would say that I am not skeptical because I work in this field, but I am cautious with the foreign ambiguous links to the rich accretions because I work in this. I know how many assumptions we do, and I mean, we can talk about it with our coffee if you want.
Okay.
But
You're also not certain about the progenitor of the white dwarf and where would water exist in the first place, right? Where your habitable zone is basically. Because the other big issue of all white dwarf research, you have basically from M dwarfs up to whatever 8 solar masses, and they all become 0.6 solar masses white dwarfs. If you see the distribution is like a super narrow Gaussian. So, like how the hell do they all end up there? We don't know. Initial final mass relation, big open question. But if you can't trace the progenitor, you don't know where to expect the planet to have water, and if that survives, and if that goes inside to be shredded, and if you can detect the water.
But these are two different things, because a water signature will happen if the body has a lot of water, like way more than the Earth. The Earth has very little water. This is talking about like something like Europa or Enceladus, which has a lot of ice, or maybe a subsurface ocean. This has to be like a lot of water in proportion to show up. Like the water on the Earth, well, it will have boiled off by the time the sun.
yeah, evaporated, yeah.
We established that.
Yeah,
We're
but
doomed.
to show water here, I think is like the rocky, the body has to have a lot of ice in the composition.
Yeah.
Not just a seal.
Okay. Any more questions? If not, let's thank again Paula. You're dismissed.